Hello everyone, welcome to UGC PG Pathshala. I am Dr. Lubna Siddiqui from Geography Department, JMI. Today we will discuss about measurement and analysis of spatial interaction, which comes under the paper Quantitative Techniques in Geography. Now, introduction. Spatial interaction is the interaction between places on the basis of movement of products, people, services, etc. in response to localized supply and demand. It is a dynamic flow process from one location to another. It is a transportation supply and demand relationship that is often expressed over a geographical space. In other words, it can be described as a realized movement of people, freight or information between an origin and a destination. Spatial interaction covers a wide variety of movements such as journey to work, migration, tourism, the usage of public facilities, the transmission of information or capital, the market areas of retailing activities, international trade and freight distribution. Economic activities are generating, that is supply, and attracting, that is demand, flows. The simple fact that a movement occurs between an origin and a destination underlines that the cost incurred by a spatial interaction are lower than the benefits derived from such an interaction. As such, a commuter is willing to derive 1 hour because this interaction is linked to an income, while international trade concept such as comparative advantage underlines the benefits of specialization and the ensuing generation of trade flows between distant locations. Spatial interaction usually includes a variety of movements such as travel, migration, transmission of information, journeys to work or shopping, retailing activities or freight distribution. Thus, it is a transport demand-supply relationship expressed over a geographical space. In addition, most spatial interaction models attempt to predict the movement of people or goods in terms of two basic factors. Although some models incorporate additional explanatory variables, these two basic factors are: number one, the distance, travel time, or more generally, impedance between the two locations, and number two, the size or some measure or prediction of the total amount of people or goods attracted to each candidate destination. Additional explanatory variables that have been incorporated in more complex model include: number one, accessibilities to capture spatial autocorrelation and or agglomeration effects, convenience or centrality. Number two, psychological boundaries such as rivers, ridge lines, railroad tracks or even major highways, which decrease the probability of interaction. Number three, demographic attributes such as the income, age or employment status of travelers. Number four, destination qualities other than its size or the number of attractions such as its walkability, diversity of land uses, etc. And number five, K factors and other spatial bias factors, which are not explanatory variables but fixed factors to account for explained patterns. It may be stated that transportation and communication systems are created or improved only after there is a demand which the new systems will satisfy. Improvement in transport system fostered the increased interactions, but they were not solely responsible for them. The leading geographers Edward L. Ullman, who worked on transport geography in the 20th century, postulated three conditions affecting transportation development, which are the fundamental conditions governing all forms of spatial interaction. They are therefore complementarity, intervening opportunity, and transferability. Let us examine each condition in turn. Number one, complementarity, that is the actual or potential relationship between two places, usually referring to economic interactions. Clearly demonstrated in the movement of crude or refined petroleum in international trade. Traditionally, Traditionally, it was assumed that interaction between the places developed because of areal differentiation in their socioeconomic conditions and different geographical background, the fact that places differed from one another. This is true to some extent, of course, but more differentiation never produces interaction by itself. For two places to interact, there must be a differentiation in demand and the supply of goods between the places. Since the demand and the supply must be specifically complementary to each other, interaction among them takes place. To take an absurd example as an illustration, if there is a shortage of meat in place A, it makes little difference that there is a marketable surplus of pulp wood in place B. The two commodities are not substitute to each other, and a flow of wood from B to A will not come about because of A's meat requirements. The two places lack a specific complementarity according to Abler, Adam and Gold. Complementarity is so important as a basis for a spatial interaction that many very low value bulk commodities can move thousands of kilometers if complementarity conditions are properly satisfied. Grain from continental interiors move to seaports, and from the ports moves by inexpensive ocean transport to markets of the other side of the world. Crude and refined petroleum products, commodities of relatively low value per unit of bulk, move enormous distances from oil fields in the Middle East, the Canadian prairies and Venezuela to industrialized areas of Europe, Japan and North America. When steel mills were built in the Chicago region, the need for coking coal was great enough to draw supplies from West Virginia despite the relatively low value of the coal and a distance over land of more than 800 kilometers. Without the specific complementarity of each supply and demand regions, the movement and interaction would never have taken place. Number 2, intervening opportunity, that is the presence of a nearer opportunity that greatly diminishes the attractiveness of sites farther away. Complementarity between places can generate interchange only in the absence of intervening opportunities. If we are considering the potential for a movement of goods from place A to place B, we have to consider any place C between them which might act as an intervening origin or an alternative destination. For example, Sikkim is closer to Guwahati than to Shimla in Himachal Pradesh, so for Guwahatians anxious to take a summer holiday to a hill station, Sikkim constitutes an intervening opportunity between Guwahati and Shimla. Intervening opportunities do not always curtail long-distance interactions. It is entirely possible that a sequence of such opportunities can help to create interactions between widely separated areas by making immediate transport links profitable and thereby paying part of the cost of the link between distant places. In a sense, intervening opportunities are like spatial sponges soaking up potential interaction between complementary places. Number 3, transferability, that is the ease or difficulty in which a good may be transported from one area to another. It is a function of three conditions, that is value, characteristics of the product, distance measured in time and money, and ability of the item to bear the cost of movement. If the time or cost of moving over distance is too much, exchange cannot occur. Besides complementarities and intervening opportunity, the third condition under which spatial interaction occurs is transferability, that is the friction of distance. Transferability is measured in aerial time and money cost. If the time and money cost of traversing a distance are too large, the movement will not take place despite despite of perfect complementarity and the absence of intervening opportunities. Instead of reaping the benefits of interaction, people will stay where they are and continue unchanged the life that they know. If goods cannot move because of their high cost of their movement, other goods will be substituted if possible, or people will just go without. Transferability differs between places, between classes of movements, and between modes of movement, and even changes with time. Thus, spatial interaction systems are influenced by three factors. Number one, complementarity, depending on areal differentiation, which results in a supply at one place meeting a specific demand at another place. Number two, the intervening opportunities between places. Number three, transferability measured in time and money cost. When spatial interactions occur, it is because each of these conditions has been satisfied. If two places have no interaction with each other, we can usually point to one or more of these factors as the reason. Thus, the amount of interaction, that is migration, travel between two places, depends upon the distance between two places, the attractiveness of each place, and the availability of intervening opportunities. Now, there are two basic types of interaction model. Number one, gravity model measures interactions between all the possible location pairs. A mathematical formula that describes the level of interaction between two places based on the size of their populations and their distance from each other. Number two, potential model measures interaction of one location with remaining other locations. It provides an estimate of the interaction opportunities available to a center of a network. Now, number one, gravity model. The gravity model is the most common spatial interaction model in travel forecasting. Gravity model as a measure of interaction has been derived from Newton's law of gravitation in physics. This principle of gravity model was first introduced in geography by Stewart, a social scientist. As applied in geography, it states that the interaction between two places, that is I and J, is directly proportional to the product of their population and inversely proportional to the distance between them, as shown in equation 1. Ij is equal to G Pi Pj upon Dij raised to the power b, where Iij denotes the interaction between I and J. Pi and Pj are population of ith and jth places respectively. Dig is equal to distance between I and j. G and b are constants. In other words, the total interaction between a place I and all other places may be given as shown in equation 2. Iij is equal to G inversely proportional to Pi Pj upon Dij raised to the power b. J is equal to 1. It is exemplified by taking case of interaction of the literate population of Guwahati city with its surrounding towns located in the part of Brahmaputra plains. It is assumed that literacy determines the intensity of people interaction in the towns in this region. As per given model, that is equations 1 and 2, the data of two attributes, namely the size of population and distance between the towns, are required to find out the intensity of population interaction of Guwahati city with the neighbouring urban centres and of Dibrugarh town of upper Brahmaputra valley for the purpose of comparison of interaction pattern. It is to note that Brahmaputra plain is a homogeneous tract of land and formed with the new alluvial soils. The economy of the plain is largely dependent on agricultural activities. However, these towns having historical impact on their economies and petroleum products and oil refineries are non-agricultural activities performed in this region and have implicit impact on spatial interaction among towns. The emerging pattern of spatial interaction is comparable to search the causes of such emerging phenomena in the region. Two examples are taken for the purpose. Example number 1, the middle part of Brahmaputra plain. Data of the magnitude of literate population and their distance of 7 urban centers of Kamrup district that is located in the middle part of the plains are collected from government offices. It is given below. Table 1 shows literates of different towns in Kamrup district, while Table 2 shows road distance in kilometers among the towns. Number 2, use of spatial interaction model. Quantitative form of the model with respect to the present case of 7 towns and for simplicity assuming B is equal to 1 and G is equal to 1 as given below in equation 3. Ij is equal to P1 P7 upon D17, P2 P7 upon D27, P3 P7 upon D37, P6 P7 upon D67, where P1, P7 are the size of town population and D is the distance between them. Interaction between the pairs of points was calculated in the following manner. As we know, Guwahati literate population is equal to 412.733 thousand persons. Rangia literate population is equal to 13.690 thousand persons. Distance between Rangia and Guwahati is 52 km. Thus, population interaction between Rangia and Guwahati is equal to 412.733 into 13.690 upon 52 is equal to 108.65 thousand persons per kilometer. In the same way, the interaction between all the other urban centers with Guwahati town have been calculated as given in diagram below. The interaction is shown in figure 1. Figure 1 shows population interaction of Guwahati city with neighbouring urban centers according to 1991 data. Now, example 2. The upper part of Brahmaputra plains. Data of two attributes, that is population and distances of all 4 towns of Dibrugarh district were collected as shown in table 3 and table 4. Table 3 shows population of different towns in Dibrugarh district in 1991, whereas table 4 shows road distance in kilometers among the towns. The interaction between Dibrugarh and remaining 3 towns of Dibrugarh district were shown in figures 2 and 3. Applying gravity model, the following population interaction were calculated as given in diagram below. Figure 2 shows population interaction map of Dibrugarh town with neighbouring urban centers in 1991. Now, interpretation. In the middle part of Brahmaputra plains, a general spatial pattern of population interaction shows that Rangia and North Guwahati town have maximum interaction with Guwahati, that is a regional center of the northeastern part of India. Noonmati oil refinery of the North Guwahati and military center located in Rangia are major reasons behind interaction in this area. On the other hand, in the upper part of Brahmaputra plains, petroleum products and oil refinery are major activities located in Dibrugarh town that attract the population of nearby towns. Dhuliajan, that is a closely located town, has highest degree of interaction with Dibrugarh. Distance and good transport connectivity are main reasons of higher degree of interaction in this region. Now, use of potential model. The total interaction per unit of population is known as potential at place I, which is denoted by Vi. Population potential Vi is equal to summation Iij upon Pi is equal to summation Pi Pj upon Dij upon Pi is equal to Pi summation Pj upon Dij into I upon Pi. Since for measuring potential Vi at place I, its population Pi will remain constant, it can be taken out is equal to summation Pj upon Dig. Vi is equal to summation Pj upon Dij, or Vi is equal to P1 upon D1i plus P2 upon D2i plus P3 upon D3i plus Pi upon Dig plus Pj upon Dij. An important point to note here is that for every Vi there is a term involving Dii, that is D11, D22, relating to the interaction of an area with itself. Since Dii is always 0, it is replaced by half of its distance with the nearest. Thus for V1 we have the following as shown in the following equation. V1 is equal to Pi upon half of the nearest distance plus P2 upon D12 plus P3 upon D13 plus P4 upon D14 plus P5 upon D15 plus Pj upon Dij. Therefore, population potential, that is population in 1000 for Rangia, that is V1, taken from the first example, V1 is equal to 13.690 upon 19.5 plus 7.707 upon 57 plus 9.902 upon 66 plus 8.563 upon 45 plus 3.381 upon 39 plus 2.923 upon 55 plus 412.733 upon 52 is equal to 0.7027 plus 0.1352 plus 0.15 plus 0.1903 plus 0.086 plus 0.053 plus 7.93 is equal to 9.25459. Or 9.25459 is the population potential value for Rangia. Figure 3 shows population potential map of Kamrup district in 1991. In the same way, population potential values for other centers of Kamrup district were calculated as Hejo 16,991.90, Swalkuchi 14,033.14, North Guwahati 27,429.06, Amingaon 31,301.37, Palasbari 18,766.22, Guwahati 56,613.41. Following the same method, the population potential values for Dibrugarh town and other centers are calculated. Dibrugarh 6,251, Duliajan 6,444, Naharkatia 5,334, Namrup 3,261. On the basis of the above calculated population potential values, the urban potential maps of Kamrup and Dibrugarh districts have been prepared using isopotential lines joining places with actual population potential values as shown in figure 4. Figure 4 shows population potential map of Dibrugarh district in 1991. The potential values as shown from the above figures indicates a much larger potential at Guwahati, that is the capital city, with a population potential value of 56,613 persons per square kilometer. It is followed by Amingaon and North Guwahati with a potential value of 31,301.37 and 27,429 persons per square kilometer. Distance has a great impact on the values of population potential. In Dibrugarh district, it is interesting to note that population potential value is highest in Duliajan town, that is 6,444 persons per square kilometer, as it is an isle township attracting heterogeneous population from northeast and all over India, followed by Dibrugarh, that is 6,251, Naharkatia, that is 5,334, and Namrup, that is 3,261 persons per square kilometer. Now, summary. Spatial interaction among the towns is described by measuring it into two ways using gravity model and population potential model. These models are mainly dependent on two attributes of urban places: the functional or population size of town, which accelerates the process of attraction, provided town functions, that is goods and services, are complementary among the towns, and the distance among towns that generally is considered in its physical term, but transport cost and travel times are also scales of distance measurement. In the model, the relationship of these attributes is established by considering its logarithmic form. In fact, mode generalizes that in a region, spatial interaction is positively related to town size and negatively dependent on distance. This relationship seems true in the case of Brahmaputra plains, as Guwahati has more interaction with North Guwahati and Rangia towns, and Dibrugarh, located in Upper Brahmaputra plain, has implicit interaction with the towns surrounded in its close vicinity. Although the experimental validation of spatial interaction techniques is gaining interest, many virtual reality researchers still consider it an art rather than a science. In the design cycle of spatial interaction techniques, the evaluation part is most often addressed in a qualitative way rather than being based on firm quantitative evidence. This multidisciplinary project has two main objectives. First, to develop a more quantitative approach to the design of spatial interaction techniques. Second, to apply and test this quantitative approach in the design of new spatial interaction techniques. I hope you have understood the concept of measurement and analysis of spatial interaction. See you next time. Goodbye. Thank you.